Okay, let's unpack this. Welcome back to another deep dive. Today, we are strapping ourselves into something fast, electric, and let's be honest, potentially lethal if you don't treat it with the respect it deserves. We are talking about student formula racing, FSAE, but we aren't talking about aerodynamics or tire compounds today.
No, we are going straight to the nervous system of the car. We're looking at the invisible force that makes these machines faster than most supercars, and more importantly, the systems that keep that force from hurting anyone.
We're diving into a document titled Thought 2026 Student Formula High Voltage Safety and Functional Safety Development Checklist.
It is a bit of a mouthful, isn't it?
It is, but
Yeah.
as I was reading through this, I realized this isn't just a rule book. It's not just a list of do this, don't do that.
Not at all.
The authors have taken a really unique approach here. They've applied a McKinsey-style framework, specifically the MECE principle, to safety engineering.
That caught my eye immediately. MECE stands for Mutually Exclusive, Collectively Exhaustive. It's a term you usually hear in, high-end management consulting boardrooms,
Right.
not in a race car garage. But it is brilliant when you apply it here.
Okay, let's break that down for the listener because it really frames everything we're about to discuss. Why would you apply a corporate strategy framework to wiring a car?
Because a high-voltage race car is just a chaotic, complex system. You have 600 volts, you have massive amperage, complex software, and you have stressed-out student engineers working on really tight deadlines.
It's a recipe for mistake.
A perfect storm. And in that environment, you have two main risks. One, your safety checks overlap. That's the mutually exclusive part.
So two systems doing the same job.
Exactly. If two systems do the exact same thing, you're just wasting weight, money, and maybe computing power. It's
Yeah.
inefficient.
But the bigger risk is the second part, right? The collectively exhaustive part.
That's the one that keeps you up at night. If your safety net isn't exhaustive, you leave a gap, a
Wow.
blind spot. You check system A and you check system B, but you forget about the interaction between them. In a spreadsheet, a gap is just a calculation error.
In high voltage racing, a gap is a fire.
Or an electrocution. It's a catastrophic failure.
So the mission of this deep dive is to look at this document through the eyes of its target audience, the chief system engineer. We aren't just ticking boxes to satisfy a judge at the competition.
No, not at all.
We are trying to build what the source calls a deterministic system. I saw that word deterministic all over the notes.
It is the holy grail of engineering. A deterministic system is one where there is zero ambiguity. Input A always, without fail, leads to output B.
No, maybe.
There is no maybe, there is no glitch. If a wire breaks, the system reacts the exact same way every single time. When you are dealing with lethal voltage, you cannot have mostly safe. You need absolute certainty.
So let's dive into this framework. The source breaks this down into a top-down structure with 6 strategic modules. But before we get to the modules, there's an executive summary that lays down the whole philosophy.
The zero compromise philosophy.
Exactly. And the core strategy they identify is that safety is a binary state.
Right. It is either 0 or 1. You are safe or you are not. There is no sliding scale, no 99% safe.
And the mechanism to achieve that binary state is the fail-safe principle.
Yeah. We hear fail-safe a lot, but let's really unpack what that means physically. It's not just a buzzword for these engineers.
Okay, so what is it?
Fail-safe means that the system's default state, its resting state, without any energy applied, is safe or off.
I think I get it. So to make the car run, to make it dangerous, you have to actively work to keep it on.
You have to apply energy to keep switches closed. Signals must be actively pulsing. You're fighting against the system's natural desire to be off.
So if a wire breaks, or a battery dies, or a connector vibrates loose,
The active effort stops.
and the car just dies.
Precisely. And because that effort stops, something like gravity or spring pressure takes over, and the system reverts to that default safe state, the car shuts down. You don't need a computer to detect the failure and say, oh no, turn off.
The failure is the off switch.
Exactly.
That leads us to the golden rule of this checklist, which I found fascinating, especially given the year is 2026. The document is incredibly strict on this. It says, critical safety logic must be non-programmable hardware.
This is the hill the author is willing to die on. And I agree with them. We live in a world where software eats everything. We are used to over-the-air updates, fixing our car's brakes.
Right.
But this checklist says, no, do not trust the code for the last line of defense.
But why is the code that bad? I mean, these are smart students.
It's not that the code is bad, it's that the medium itself is fragile. Microcontrollers are incredibly complex. They rely on memory fetching, instruction decoding, clock
A
cycle.
lot of things have to go right.
A million things have to go right every second.
Uh-huh.
A microprocessor can hang, it can get stuck in an infinite loop. A cosmic ray from deep space can literally flip a bit in its RAM and corrupt a variable.
Wow.
It happens. So if your emergency stop relies on a line of C++ code executing perfectly at the right microsecond, you have introduced a probability of failure.
But a physical resistor.
A resistor just is. Physics doesn't crash. An analog circuit using things like comparators and voltage references, it just follows the laws of physics instantaneously. It doesn't need to reboot.
It's deterministic.
It is deterministic. That is why the last line of defense, things like the brake plausibility device and the insulation monitoring, they must be pure hardware.
Okay, so that's the philosophy. Binary safety, fail-safe, and hardware first. Now let's walk through the 6 modules of this top-down checklist. Section 2 starts with Module 1 HV Awareness and Indication.
Or as I like to call it, visibility.
Visibility.
Before you even touch the car, how do you know if it's a harmless pile of carbon fiber or a charged weapon waiting to go off?
The primary tool for that is the TSAL, right? The Tractive System Active Light.
Yep. The big flashing light on the roll hoop. Red means danger, HV is active, green means safe.
In theory.
In theory. But the checklist immediately asks a very uncomfortable question. Why is the light red? How does the light know?
What do you mean?
A common mistake rookie teams make is trusting the inverter. The inverter is the big computer box controlling the motor. It talks to the car's central ECU via the CAN bus.
Okay.
So the ECU asks, hey, inverter, is there voltage? The inverter software says yes, so the ECU software turns on the red light.
That sounds reasonable. Why is that a problem?
It's a fatal flaw. What if the CAN bus wire is broken? What if the inverter's processor has frozen?
Right.
The inverter might have 600 volts sitting in its capacitors ready to kill you.
It's not reporting it.
It can't. The communication line is dead. The ECU hears silence, assumes no voltage, and keeps the light off. Or worse, it turns on the green light.
And then a student walks up, sees a green light, thinks the car is safe, touches the tractive system.
And gets 600 volts.
Exactly.
So the checklist imposes a hard rule: independent voltage sensing.
Independent.
You must measure the voltage directly. You need a separate dumb analog circuit that physically touches the DC link, the main power rails. If that circuit sees more than 60 volts, it hardwires the red light on. It bypasses the computer entirely.
It doesn't ask permission, it just does it.
Physics commands it.
There's also a note here about power redundancy. They call it the zombie car scenario.
Yes, this is another nightmare. Imagine the car's low-voltage battery dies. This is the little 12V or 24V battery that runs the dashboard, the computer, the lights.
Okay, the brain of the car.
Right. If that battery dies, the dashboard goes dark. The car looks completely dead. But the high-voltage battery pack is a completely separate system. It could still be connected and live.
So you have a dark car that is secretly alive.
The ultimate trap.
Yeah.
So the checklist suggests powering the red TSAL light via the high voltage itself through a voltage divider or some other independent secure source.
So the danger itself powers the warning.
The danger itself provides the energy to warn you of its presence. It's a beautifully simple, robust solution.
That is clever. What about the green light? The system's safe indicator.
The logic here is even tighter, as it should be. To show a green light, 2 things must be physically verifiably true.
What are they?
1, the ARs, the accumulator isolation relays, those big main switches in the battery pack, must be physically open. We confirm this with auxiliary contacts, which are tiny mechanical switches literally attached to the main relays.
So you're not just assuming they opened, you're checking.
You're checking a physical switch. And 2, the voltage in the inverter, measured by that independent sensor, must be below 60 volts.
So AR's confirmed, open and voltage confirmed, low equals green.
Correct. But here's the really smart part, the latching logic. Suppose the car gets confused. Suppose the AR's auxiliary contacts say they're open, but for some reason, the voltage sensor is still reading 400 volts.
That shouldn't be possible.
It shouldn't be. Maybe a contactor is welded shut. The hardware logic sees a contradiction. It can't be both open and have voltage.
So what does the light do? Flash yellow or something?
It turns off, and it stays off. It latches into the default state, which is no green light. If the car cannot mathematically, physically prove it is safe, it must not claim to be safe.
It's that binary philosophy again. 0 or 1, safe or not.
There is no middle ground.
Moving on to the other critical part of Module 1, the IMD, that's the insulation monitoring device.
This is the guardian angel of electric racing. In a consumer EV, and in these cars, the high voltage system is floating. It doesn't use the car's metal chassis as a ground return path like a normal 12V system.
Shows a closed loop.
It's a closed loop. If you touch the positive terminal, theoretically nothing happens because you aren't completing a circuit to the negative terminal.
Yeah.
But what if a wire frays and touches the carbon fiber or metal frame?
The frame itself becomes live.
The whole car is a trap.
No.
If you touch the car and you're standing on the ground, you complete the circuit through your body.
Oh, this is bad.
Very bad. The IMD's only job is to watch for this leakage. It constantly measures the electrical resistance between the high voltage lines and the chassis.
And the source document is specific. It mentions the Bender IR155-3204.
Yeah, that's the industry standard. Or a certified equivalent. You can't just build your own.
And the threshold is strictly defined. It has to react at less than 500 ohms per volt.
Right, so for a 600-volt system, if the resistance between HV and chassis drops below 300,000 ohms, that's 300 coulombs, the IMD has to trip.
That sounds like a lot of resistance still.
It does, but at 600 volts, even a tiny current can be lethal. So the threshold is very, very sensitive.
Now, here is the detail that really highlights that pure hardware rule we talked about, the decoding strategy. The IMD communicates with the car using PWM pulse width modulation.
It sends a square wave signal, a blinking light, electrically speaking.
And this is where so many teams fail scrutineering.
This is a classic failure point.
Yeah.
The IMD outputs a specific frequency. 10 hertz means I'm working, everything is fine. 50 hertz means ground fault, panic. And 40 hertz means there's a problem with me, the IMD itself.
So logically, you just feed that signal into your microcontroller and write a simple bit of code.
If frequency, it's easy.
And that is exactly what this checklist forbids you from doing.
Why? That seems so simple.
Because again, you are relying on code. You are relying on the MCU's timer interrupt to measure the pulse width correctly. What if the processor is busy servicing another task? What if the interrupt priority is wrong and it misses a few pulses?
It might misinterpret the signal.
You might think 50 hertz is 10 hertz and do nothing while the car is live. The checklist demands a hardware frequency to voltage converter. It even suggests a specific chip, the LM2917.
And how does that work?
It's a beautiful, simple analog chip. It takes the pulses in. If the pulses come faster, meaning a higher frequency, it outputs a higher DC voltage. If they come slower, it outputs a lower voltage.
So it translates frequency into a voltage level. Yes. It turns that 50 hertz danger signal into, say, 5 volts DC. Then you use a simple hardware comparator, another dumb chip, that has one job. If my input voltage is greater than 4 volts, flip this switch. And that switch is in the shutdown circuit.
No code, no booting up, just physics. Signal in, reaction out.
It removes the interpretation layer. It removes the possibility of a software bug ignoring the fire alarm.
That is incredibly robust. Okay, let's move to section 3. Module 2, critical logic and intervention. These are the kill switches, the things that stop the car when physics goes wrong or the driver panics.
Right.
First up, the infamous BSPD, the brake system plausibility device.
This is a rule born from real-world accidents and near misses.
Yep.
Imagine a throttle pedal gets stuck mechanically, or the sensor fails in the full throttle position. The driver takes their foot off the gas, but the car just keeps accelerating.
So what's the driver's first instinct?
They stomp on the brakes. Hard.
So now you have the electric motor at full power fighting the mechanical brakes.
A battle the motor often wins, or at least it causes the brakes to overheat and fail completely. The BSPD is designed to catch this specific nightmare scenario.
The logic is, if brake pressure is high, the rule says over 30 bar power to the motor is high, over 5 kilowatts.
Then the car is in a contradictory, dangerous state.
Exactly. But there's a time element.
Right. We allow for a momentary overlap. Maybe you're doing a fancy left foot braking maneuver or a hill start. But if that condition braking and power lasts for more than 500 milliseconds, half a second.
The BSPD must kill the power to the motor instantly.
And again, the source document is practically screaming it off the page. Pure hardware.
No microcontrollers.
0. You cannot digitize the brake pressure signal and compare it in software. You need an analog comparator circuit on the pressure sensor's voltage output, another analog comparator on the motor's current sensor voltage, and a physical timer circuit.
A physical timer? You mean like an hourglass?
Hey, effectively, yes.
Okay.
An electronic hourglass. It's an RC network, a resistor and a capacitor, or a dedicated chip like a 555 timer.
How does that work?
When the fault condition starts brakes, and power on current starts to flow through a resistor and slowly fill up the capacitor, it's designed so that it takes exactly 500 milliseconds for the capacitor to charge up to a trigger voltage.
Ah, I see.
If the fault goes away before 500 meters, the capacitor drains back to 0. No problem.
Huh?
But if the fault stays, the capacitor hits that voltage limit, it triggers a latch, and bam, shutdown circuit is opened.
Here, the source mentions latch and reset. This is critical. Once it trips, you can't just lift off the brake and keep driving.
Absolutely not. That would be so dangerous because the underlying problem, like that stuck throttle, might still be there. If the DSPD trips, the system must latch open. The power stays off.
And the only way to reset it
Is to power cycle the entire low-voltage master switch. Let's turn the car completely off and on again. This forces the driver and the team to stop and acknowledge that a serious fault occurred.
There's a really great practical tip here, too. Design a test button right on the PCB for the BSPD.
Yes. Scrutineers, the judges who inspect your car, they love this. They don't want to have to get in the car and do a burnout against the brakes to test if your BSPD works.
That seems unsafe.
It is.
Yeah.
So instead, you give them a little button. They can press the brake pedal with the car stationary, then press your test button, which simulates the high power signal. If the main contactor clicks open, you pass.
It shows you've thought about testability from the start.
It makes you look like a pro.
Let's talk about the shutdown circuit, SDC itself. This is the backbone of the entire safety system.
It is. The best way to think of the FTC is a giant single loop of wire that runs all around the car. It's a series topology.
The source uses the analogy of old-school Christmas lights.
It's a perfect analogy. If one bulb burns out, the whole string of lights goes dark.
And in this case, the bulbs are all the safety switches.
Exactly. You have the emergency stop buttons, the big red mushrooms, one in the cockpit, two on the outside of the car. You have the inertia switch, which trips if you crash. You have the output from the BSPD circuit, the output from the IMD, the output from the battery management system.
They are all just switches wired in a line, one after another.
In series. So if any single one of them opens for any reason, driver hits the E-stop, car crashes, IMD sees a fault, the loop is broken. The current stops flowing.
And what is at the end of that loop? What is it powering?
The coils of the airs, the big contactors inside the battery. They need a constant flow of current through their coils to stay magnetically closed.
So if the SDC loop breaks anywhere?
The current to the air coils is cut instantly, and they are spring-loaded.
Ah, so it's purely mechanical at that point.
Yes, powerful springs physically snap them open. That's the fail-safe design. You cut the power, the springs take over, and the high voltage is trapped safely inside the battery box. The rest of the car is de-energized.
This module also mentions HVIL, that's the high voltage interlock. It sounds similar to the SDC, but for the connectors.
It's a parallel concept, but for a different purpose. The HVIL is another safety loop, but this one runs specifically through every high voltage connector and every lid on an HV enclosure.
So if I try to unplug the big orange cable going to the motor, or if I try to unscrew the lid of the inverter while the system is live,
You break the HVIL loop, which in turn is part of the main shutdown circuit, so it opens the ARs.
why is that necessary? If I unplug it, the power stops flowing anyway, right?
Yeah, eventually. But have you ever pulled a plug on a running vacuum cleaner and seen a little blue spark?
Yeah, of course.
That's maybe 120 volts and a few amps. Now imagine doing that with 600 volts and 200 amps. If you pull that plug apart while high current is flowing, you don't get a little spark, you draw an electric arc.
Like a welder.
Exactly like a welder.
Yeah.
It's a mini lightning bolt. It can melt the connector pins, create a fire, blind you with UV light, or electrocute you.
So the HVIL prevents that arc. How'd you?
Through clever mechanical design. It's called last mate, first break. The connectors have special pins for the low voltage HVIL loop that are physically shorter than the main high voltage power pins.
Oh, I see where this is going.
When you start to pull the plug out, the short HVIL pins disconnect first,
Before the big power pins have fully separated.
milliseconds before. This breaks the safety loop, which kills the power to the ARs, which snap open and cut the current flow at the source.
No.
By the time the middle power pins actually disconnect from each other, there's no more current flowing. No energy, no arc.
That is just cool engineering. It anticipates a human error, someone forgetting to turn it off before unplugging, and uses simple geometry to fix it.
Exactly. It makes the system idiot-proof. Or, to be more polite, operator error tolerant.
Okay, let's move to Section 4, Module 3, HV Distribution and Protection. This is about managing the flow of all this energy. We've mentioned the ARs, the contactors, but the checklist gets specific about which ones to use.
You can't just go to an auto parts store and get a standard relay. You need a contactor specifically rated for breaking a DC, or direct current, load. The source suggests parts like the Gigavac GX14 or the TE-EVC 250.
What's the big difference between switching DC and AC?
AC. Alternating current, which is what's in your house, crosses 0 volts 100 or 120 times every second. If an arc forms when you open a switch, that natural zero crossing helps to extinguish the arc. It kills it for a moment.
But DC doesn't do that.
DC never crosses zero. It is a relentless unidirectional stream of pressure. If you try to open a switch on high voltage DC, the arc will form, and it will just stretch and sustain itself. It will burn the switch contacts down to nothing.
So how do these special contactors deal with that? It says a magnetic blowout.
It's as cool as it sounds. They have powerful permanent magnets built into the switch housing, right next to the contacts. When the arc forms, the magnetic field pushes the plasma of the arc sideways and outwards, stretching it until it becomes too long and thin to sustain itself, and it snaps.
It literally blows the arc out like a candle.
That's the perfect way to think about it.
That is metal, both literally and figuratively. And there's a note here about using economizers. What's that?
These big contactors take a lot of power to pull closed against their springs. Maybe 2 or 3 amps at 12 volts. But once they're closed, it takes very little power to hold them there.
Okay.
If you keep pumping that full 3 amps in, you just waste energy, drain your low-voltage battery, and the coil gets really hot. An economizer circuit hits the coil with full power for a fraction of a second to close it, then immediately drops the current down to a holding level using PWM.
So it saves energy and reduces heat.
Exactly. It's an efficiency and reliability improvement.
Okay, let's talk about the fuse, the ultimate last resort failsafe.
The fuse is there for when everything else has gone wrong. The contactors have welded shut, the software has gone crazy, there's a dead short. It's the one-time use device that saves the car from burning to the ground.
And again, it has to be a special DC-rated fuse.
Yes. Rated for DC and a voltage higher than your system voltage. A common and very dangerous mistake is using an AC fuse from a hardware store. An AC fuse on a major DC short circuit might literally explode rather than melting safely.
And its location is critical.
The checklist is very clear. Most upstream current of the positive terminal. It has to be the very first thing the current touches as it leaves the battery cells. It protects absolutely everything downstream from that point.
Now, pre-charge and discharge. This is about turning the system on and off smoothly. Why do we need to pre-charge? Why can't we just slam that main switch closed?
Because of the huge capacitors in the motor inverter. Capacitors are like empty water buckets. When you first connect them to a high-voltage battery, they want to fill up instantly.
So they draw a huge amount of current.
A massive amount. It's called inrush current, and it can be thousands of amps for just a microsecond.
Like opening a floodgate into an empty reservoir.
Exactly. And that huge surge of current is more than enough to spot weld the metal tips of your main contactor together.
And then you can't turn the car off.
Now your car is stuck in the on position. The pre-charged circuit prevents this. It uses a smaller secondary relay and a big resistor to fill those capacitors slowly, like using a garden hose instead of a fire hose.
So you fill them up to about 95% of the battery voltage?
Right. And once the voltage is equalized, then you close the main contactor. There's no voltage difference, so there's no big current surge. It closes gently.
And discharge is just the opposite problem.
Yes. When you hit the e-stop and the ARR is open, the battery is disconnected, but the capacitors in the inverter are still full. You've got 600 volts just sitting there in the car.
That's a huge hazard for a mechanic or a trackside worker.
A deadly one. The rules say the voltage must drop below 60 V within 5 seconds.
How do we guarantee that happens every time?
With an active discharge circuit. You need a circuit that bleeds that stored energy off, usually through another big resistor, turning it into heat. But here's the clever MECE failsafe part. How do you trigger it?
You could have a microcontroller send a signal when the car turns off.
No. Again, no software. What if the microcontroller is the thing that crashed? You use a normally closed relay.
Normally closed.
It's a type of relay that is physically connected or closed when it has no power going to it. So while the car is running, you are actively powering this relay to hold it open to keep the discharge resistor disconnected.
I see.
The moment the car dies, or the shutdown circuit opens for any reason, the power to this discharge relay's coil is cut. It loses its magnetic field, and a spring snaps it back to its normal state, which is closed.
And that connects the bleed resistor across the capacitor.
Instantly and automatically. So if the car loses all power, it automatically makes itself safe by draining the stored voltage. It requires energy to remain dangerous.
It defaults to safety.
Every single time.
Okay, let's move to Section 5, Module 4, Thermal Safety. Batteries get hot. And when they get too hot, fire is bad.
Fire is very bad. This section is particularly important because it addresses some critical updates in the regulations, specifically a rule called EV 5.8, which is all about temperature monitoring.
The checklist has this in bold. Sensors must physically touch the cell negative terminal or the bus bar. Why so specific?
This is a vital detail. Some teams, trying to save time or money, will just tape a thermistor to the outside plastic shrink wrap of the cell. But plastic is a thermal insulator. It doesn't conduct heat well.
So it's a delayed reading.
A dangerously delayed reading. By the time the plastic casing gets hot, the chemical core of the cell is already melting down.
And why the negative terminal specifically?
In most cylindrical cells, like the 18650s or 21700s that many teams use, the entire outer metal can of the cell is the negative terminal. It's the most direct thermal path to the internal chemistry roll.
So you're getting the truest, fastest temperature reading.
As close as you can get without putting a probe inside the cell.
And what about coverage? The rules say you only need to monitor 30% of the cells.
The rules say 30%, yes. But this chief architect recommendation, this MECE approach, says 100% coverage. No question.
Why? If the pack is designed well, shouldn't they all be around the same temperature?
They should be. But a battery pack is a chain, and it's only as strong as its weakest link. If just one cell has an internal manufacturing defect and starts to go into thermal runaway, it doesn't matter that the other 99% of the cells are cool.
That one cell will ignite its neighbor.
And then that neighbor ignites its neighbor. There's a chain reaction, a domino effect.
And with only 30% coverage, you could have a blind spot.
You're guaranteed to have blind spots. 100% coverage creates a truly exhaustive MECE view of the pack's thermal health.
And if any one of those sensors gets too hot, the threshold is 60 degrees Celsius.
It's a hard cutoff. The BMS, the battery management system, must have a hardware output that directly opens the shutdown circuit.
Not a CAN message.
Never a CAN message. You do not send an email to the fire department. You pull the physical alarm handle.
Let's talk about physical protection, the firewall.
This is literally a wall between the driver's back and the battery box. The rules are specific. It needs to be made of a UL94 V0 rated insulation material.
Which means it's self-extinguishing plastic.
Right. It won't sustain a flame. And that needs to be backed by a grounded aluminum plate.
Why grounded?
Two reasons.
Okay.
First, for EMC shielding, which we'll get to. But second, if the battery has a catastrophic failure and a live bus bar comes loose and touches the firewall, you don't want the firewall itself to become electrified and shock the driver.
So the grounding ensures that if a high voltage wire hits that plate, it just shorts to ground and blows the main fuse.
Exactly. It contains the electrical fault.
And venting is the last part here?
Batteries vent hot, flammable, toxic gas when they fail. You need a plan for where that gas goes. You need burst discs or one-way valves and a dedicated physical path that guides that gas out the back or side of the car safely away from the driver.
You cannot have that gas leaking into the driver's helmet area.
Absolutely not. That's a disaster.
Okay, Section 6, Module 5, Environmental and EMC Robustness. This is about making sure the car survives the real world. Rain, vibration, and the invisible storm of electromagnetic noise.
The rain test is a classic and often feared part of FSAE scrutineering. They literally spray the car down with hoses for 2 minutes. If your IMD trips, you fail. You're done.
So waterproofing is non-negotiable. The standard is IP67.
Right. IP67 means it's totally dust-tight and can be immersed in water up to 1 meter deep. Every external connector, every enclosure has to meet this. But here's the subtle detail that trips people up. Gore vents.
Like the stuff in my Gore-Tex jacket.
It's a similar principle. If you build a perfectly sealed, airtight battery box, what happens when the car runs and the batteries heat up?
The air inside expands. It creates pressure.
A lot of pressure. And that pressure will find the weakest point in your seal and blow it out.
Yeah.
Then when the pack cools down, it creates a vacuum that actively sucks water in past the now damaged gaskets.
So you need the box to breathe, but not drink.
Perfectly put. A Gore vent is a membrane that allows air molecules to pass through to equalize the pressure. But the pores are too small for larger water molecules to get in. It breathes air, but blocks water. It's essential for maintaining your seal integrity over many heat cycles.
Now, EMC, electromagnetic compatibility. This is the dark art of electrical engineering.
It really is. A high-voltage inverter switching hundreds of amps at 10 or 20 kilohertz creates a massive amount of electrical noise. It's like a powerful radio jammer sitting right next to all your delicate sensor wiring.
And that can cause phantom readings or even shut the car down.
It absolutely can. The way we fight it is with proper shielding and grounding. The checklist has a very specific rule. High-voltage cables must have a braided shield, and that shield must be grounded at both ends.
Both ends. I've always heard that grounding a shield at both ends causes ground loops.
It does, for low-frequency noise. But for the very high-frequency noise that an inverter produces, grounding at both ends is essential. It makes the shield act like an extension of the chassis, a Faraday cage, that contains the electrical noise inside the HV cable and prevents it from radiating out.
But for the low-voltage signal cables,
For your sensitive analog signals, like the throttle pedal or wheel speed sensors, you ground the shield at single end only. This prevents those low-frequency ground loops, where tiny differences in voltage across the chassis can be picked up as signal noise.
so it's a different strategy for a different problem. HV equals 2 ends, LV equals 1 end.
That's the rule of thumb. And all those LV grounds should ideally meet at one single point on the chassis. It's called the star point.
Why is that so important?
If you ground your ECU at the front of the car and your sensors at the back, the tiny electrical resistance of the chassis itself means there can be a small voltage difference between the front and back. The system can interpret that voltage difference as part of the signal corrupting your readings. A single star point eliminates that problem.
And there's a quick, super practical tip from the source here. Sand off the anodized layer.
Oh, this one kills so many teams their first year. Aluminum chassis parts are often anodized, which gives them a nice color and corrosion resistance, but that anodized layer isn't oxide. It is non-conductive. It's an electrical insulator.
So you bolt your main ground lug onto this beautiful black anodized frame.
And you have no ground connection at all. You have to physically sand it or grind it down to the bare, shiny metal to get that good electrical connection, that resistance of less than 300 milliamps that the rules require.
Finally, we arrive at Section 7, Module 6, Software Control Safety. We've spent most of this deep dive saying don't trust software, but we still need it to actually drive the car.
We do. Software is what controls the torque. It's what makes the car fast and responsive. But we need to wrap that performance-critical software in its own layers of safety. You can't just have one sensor on the gas pedal. What if it breaks and its output signal gets stuck at 100% throttle forever?
You'd have a runaway car.
Exactly. So you must have two independent sensors,
Redundancy.
and not just two of the same kind. Ideally, they work inversely. One goes from 0 to 5 volts, the other from 5 to 0s, or they operate on different scales. This way, a simple short circuit to power or ground doesn't affect both sensors in the same way.
And the software is constantly comparing them.
Constantly. The rule is, if the two sensors disagree by more than 10% from within 100 milliseconds,
Oh, kill the torque. Set it to 0.
precisely, the car's VCU, the vehicle control unit, has to assume the sensors are unreliable and shut down the power until the fault is cleared.
And there's also brake override.
This is the software backup to the hardware BSPD we talked about earlier. It's a simpler check. If the software sees any brake pressure being applied, and Dories is asking for torque with the accelerator, the software must prioritize the brake. It must zero the torque command to the inverter,
It's a second layer of defense.
a belt and suspenders approach.
Now, system monitoring. This gets into the health of the computer itself, the
Yeah.
watchdog.
Right. Who watches the watcher? The VCU is the brain of the car. But what if the brain has a seizure? What if the software code gets stuck in an infinite while true loop?
The car would just keep doing whatever it was doing in that last millisecond, which might be full throttle.
Exactly. So you need an external hardware watchdog. This is a separate, simple little chip. The main complex CPU has to send this little chip a kick or a pulse. Every few milliseconds, it's constantly saying, I'm okay, I'm okay, I'm okay.
And if the main CPU freezes and stops sending those kicks,
The watchdog chip waits a specific amount of time, say 50 milliseconds, gets no signal, assumes the CPU is dead, and then it pulls the reset line on the CPU, forcing a reboot. Or, in a more critical system, it could directly cut power to the motor outputs.
it's a dead man switch for the processor.
That's a perfect description.
And finally, heartbeats on the network.
This is for the CAN bus communication. The inverter is constantly listening for torque commands from the VCU. Go 50 newton meters, go 60 newton meters. If the CAN wire breaks or the VCU dies completely, the inverter stops receiving new commands.
So what should it do? Should it keep applying the last command it got?
Absolutely not. That's incredibly dangerous.
Mm.
The rule is that if communication from the VCU is lost for more than, say, 50 or 100 milliseconds, the inverter must be programmed to self-zero the torque.
It has to assume that silence means stop.
Yeah, it all comes back to that core fail-safe philosophy. Silence equals stop. A disconnected wire equals stop. A frozen computer equals stop.
That is the definition of a deterministic safety system.
It is.
This has been a massive deep dive. We've covered everything from the flashing lights on the roll hoop to the sub-millisecond timer circuits on a PCB.
And if we zoom out again, looking at this from that chief architect perspective, the conclusion is crystal clear. This checklist isn't just about passing inspection. It's a blueprint for reliability.
The source material puts it so bluntly, I have to quote it. A finished 40-kilowatt car beats a broken 100-kilowatt car every time.
It is the truest statement in all of motorsport. A 100-kilowatt car that triggers a false BSPD fault every other lap, or that overheats its contactors, or that fails the rain test, is useless. It just sits in the paddock.
While the slower, more reliable car is out there racking up points.
A 40-kilowatt car that is robust, deterministic, and has been rigorously tested will finish the endurance race. And to finish first, you must first finish.
And there's one final piece of advice from the document that ties this all together. AL testing.
Hardware in the loop. This is so critical. Do not test your critical safety logic for the first time on the racetrack with a student driver strapped into the car. That is irresponsible.
You have to test it on the bench first?
You build a test bench, you make the car's computers think they're driving, you inject faults, you have a switch that simulates a broken wire, a dial that simulates a stuck pedal sensor, a heat gun to simulate an over-temperature battery.
You try to break it in the lab.
You verify that the hardware clicks off, that the relay's open every single time, under every fault condition you can imagine. Only then, when you have that confidence, do you put wheels on the ground.
It's rigorous, it's methodical, and it's the only way to build a car that's not only fast, but safe enough to be fast.
And honestly, it's the only way you can sleep at night as an engineer, knowing your driver is protected by physics, not just by code.
Well, there you have it. The top-down MECE breakdown of the 2026 High Voltage Safety Checklist, a roadmap for building a beast of a machine that respects the laws of physics and the fragility of software.
It's a great example of how applying a rigid structure, like that McKinsey framework, can actually liberate you to push the performance limits, because you know your safety net is solid and have no holes.
Thanks for tuning into this deep dive. Whether you're building a Formula student car or just, wiring up a toaster, remember, design for failure so that you can succeed safely. See you next time.
Stay safe out there.